Hello and welcome to our talk, which is about what we hope will be an interesting new benchmark problem, the puzzle video game plotting. This is a video game released in 1989, and the objective is fairly simple. It is to reduce a given grid of color blocks down to a goal number or fewer, and all that we have to do in order to do that is move the little avatar guy you see in the diagram there up and down and shoot the blocks it holds, in this case horizontally rightwards. That means the block will either hit the grid directly or it will hit some of those blocks you can see above the grid and bounce downwards into the grid, so hit it vertically. And there are various rules about how the grid responds to being hit like this. So let's quickly summarize them. If the block hits a wall that is traveling horizontally, it falls vertically downwards. If it falls onto a wall, or on the floor indeed, it then rebounds into the avatar's hand. If the first block that we shoot hits is of a different type, so a different color from itself, then it just simply rebounds into the avatar's hand and the grid is unchanged. This is essentially a null move, which we'll be disallowing in our models. If, on the other hand, the block that we shoot hits a block of the same type, that is the same color, then the block that is hit will be consumed and our block will continue in the same direction. Everything above the block that was consumed will fall by the action of gravity, as you can see in the example at the top right there. This can also happen vertically, so if we shoot a block downwards into the grid and it hits something of the same color, the first thing it hits, then it will consume that and it will continue. Now, after we've shot a block and it's consumed something of the same type or color, and then it hits something else, another block with a different color, this is what happens. The block that we originally shot will replace the different colored block in the grid, as you see in the example there, and that different colored block will itself bounce into the avatar's hand. And finally, there is one extra thing to consider, that in this case, where the block that we've shot reaches the wall, maybe it's consumed some blocks on the way, and then falls, it can actually continue to consume blocks of the same color as it continues to fall. And this means that we can consume blocks both horizontally and vertically at the same time. This is quite tricky, of course, to model, and that's one of the challenges that we face. Okay, so quite a difficult, or quite a complex set of state changes there to cope with. In passing, though, we know that this is a planning problem in the AI planning sense. We have an initial state that we're given, which is our initial grid, and we have some goal states that we want to reach. These are not usually unique because all we're saying is that we want a certain number of blocks remaining, but we're not saying exactly what that configuration is. And the sequence of actions to get us from this initial to our goal state is just simply which are the shots that we have taken. And we're going to try and model this in two ways. Firstly, with a constraint modeling language, Essence Prime, and secondly with the planning domain definition language, otherwise known as PDDL. This is the standard to input to automated planners, but there are different fragments of PDDL with different features, and we're going to adopt the one which is most commonly supported. Now, both of these models are quite long. We will give an outline. The full details, of course, are in the paper. The Essence Prime model then could be said to take a state and action approach, which means we have decision variables that represent the state of the grid and the hand of the avatar at each time step, starting of course with the initial state, and we also have decision variables to represent the action that we take to transform the preceding state into the succeeding one. Because the plan length is unknown, we make the length of the plan a parameter and ask for a plan of exactly that length. Therefore, we can solve separate instances increasing n until we find a solution for a particular n. The modeling here, as we'll see, is aided by fairly good support in constraint modeling languages for arithmetic and the data structures, so for example a matrix, which can be used to model the state at particular time steps. In PDDL, we have some advantages. So for example, because it knows it's a planning problem, it copes automatically with the fact that the length is unknown and we don't need to model time steps explicitly. But the modeling is inhibited by fairly limited arithmetic in the common version of PDDL that we're using and by limited data structures. So let's begin with the Essence Prime model. the basic viewpoint is fairly straightforward. We've got variables to represent the shots that we take at the top there, and also variables that represent the grid and the hand, again, at each time step. There are some more variables which deal with that special case I mentioned, where we can fire along an entire row and then down a column, but for those, please see the paper. So to represent or constrain the goal state in this model is very straightforward. All that we're really doing is counting the number of empty blocks there in the final state after the final action, and it has to be a certain number or fewer, or greater, sorry, for emptiness. And we're also going to constrain the actions so that something interesting has to happen at each time step. And we're just doing that by saying, again, we're going to have to reduce the grid by at least one block at each time step. You'll have noticed that we use two variables for firing, one that says which row is it and which column is it. Of course, we must fire either horizontally or vertically, but not both, and this simple constraint makes that happen. And that's the basics. Then after that, we need to constrain the more complex transitions of the state. And as you'll see in the paper, these are all stated in an if and only if form to make sure that no part of the state is left unconstrained. Otherwise, the constraint solver might put some spurious values in the state, which is obviously no good. And we've subdivided these into four cases. Either the hand is unchanged, or a grid cell becomes empty, or a grid cell stays the same because it's not affected, or a grid cell changes its color from something other to something other than empty. This might affect the hand. So these are the four cases that we have. We're going to look first at the hand unchanged case, and this itself is split into two different cases, which are relatively straightforward. So if we require that a move does something useful, then these are our two options. Either we're going to fire down a column containing only the same color blocks as the block fired, in which case the block will hit the floor, and that same colored block will get back into the hand, or we're going to fire along a row, all of the same color or empty, hitting the wall, then consuming everything beneath it on that rightmost column before hitting the floor and ending up back in our hand. So two fairly restricted cases. This is how we're going to write that down. You can see the if and only if style at the top there. So this is just saying that, well, the hand in this time step is the same as it was in the previous time step. And you can see from the comment there, the first part is about firing down the column and then hitting the wall. And basically it says, let's loop over the particular cells in that column that we're talking about and say, well, it's either the same color as the hand, so it will be consumed, or it's empty, so we just pass straight through it. So that's one of the conditions. The other case, as I've said, is for when we shoot rightwards through things which are all the same color. So that's the two subcases that you see here. We're going to say that everything in that row that we're shooting along is either, again, empty or the same color as the hand. And then we're going to have to go down that final column where, again, everything either has to be empty or the same color as the hand, in which case that block will appear back in the hand of the avatar according to the rules. So there are three other cases. As I mentioned, these are stated similarly in a sort of similar style as you've seen there. They are longer and more complicated, and you can see them in their full detail in the paper. Looking now at the PDDL viewpoint, we are going to first establish the basics of that. So we use two types, color and number, unsurprisingly to represent the color of things like the cells, either in the hand of the avatar or in the grid, and numbers to represent the indices of rows and columns. So the state that we're going to carry around with us is the color of the block in the hand again, and the color of each cell in the grid. We're going to use null for empty. Arithmetic is tricky in this fragment that we're using. Basically what we have to do is define all the numbers that we're going to be interested in using, and then some extra predicates like successor, less than, and distance to give us enable us to represent the preconditions and effects of our actions. So the actions that we introduce, again, correspond similarly to the cases that I showed you in the essence prime model there. We can shoot along a row partially, we can shoot down a column, we can shoot, in that special case, along a row and down a column, we can shoot an entire row, and those have been subdivided into these 4. Again, we're going to look at the first of these, and the rest can be found in the paper. So we have a fairly similar structure to what we saw in the essence prime there. You can see some parameters at the top of this action specification, and essentially the planner is going to instantiate these as it selects an action. So here we've got which row are we talking about, which cell are we going to reach up to when we're shooting along a partial row, and the color that we're talking about as well. And you can see there that what we're going to require is that there exists a column next to the limiting cell which is a different color, so that's going to say we can shoot along a row so far but no further, and all the blocks up to there have to be of the same color as what's in the hand or null. If that's the case, then we've successfully shot along the row, and then we're going to specify the effects, and that essentially swaps the contents of the hand for the thing that we shot up to in the grid, and changes the grid cell appropriately. Okay, so again, the rest of the cases are given in full detail in the paper. Let's talk about what we found experimentally. The performance of PDDL with a state-of-the-art planner fast downward was not very good, and is only able to solve 3x3 instances within an hour's timeout. And really the problem is the size and the complexity of the model I've just talked about. It had a lot of trouble grinding it out before it got any search done, and therefore that limited the instances that it could solve. We had more success with the constraint model using Savile Row to grind it out to SAT, and using the Cadical solver. As you can see in the table there, we generated some square instances with increasing numbers of colors. The model is quite complex. You can see that the pre-processing times of the work that Savile Row has to do is it's not inconsiderable, but once the instance has been ground out to SAT, the performance is relatively respectable. So in summary, we've seen a case study of a new benchmark plotting. It's a planning problem characterized by quite complex state transitions following each action. We saw that when we tried to model this in PDDL, in the commonly adopted fragment of PDDL, then it's not really very well suited for expressing these state transitions, and as a result, the planner really did struggle to solve instances of any particular interest. It's slightly more easy to write down in constraint modeling language terms, particularly because we have arithmetic and a bit more in terms of data structures. Although, again, if we had a bit more to the language in terms of planning constructs, that also would make it easier still. It should be said that this is a fairly basic model even now, and there's plenty of scope for adding symmetry breaking, exploiting dominance in plotting. When we have done so, it would be non-surprising to find that these constraints are much easier to state in the constraint modeling language than in PDDL. Thank you very much.